Hello, hello. Excuse me. Mexican flavor today? Oh, you're talking about the music? I'm listening to these upbeat lo-fi mixes. It's really fun. Lo-fi music is usually a little more reflective, subdued, and this is like happier lo-fi music. How are you doing today, Phil? Nice. How's the project going? You're at part 3. There's only 3 parts, right? Let's see. Oh no, there's 4 parts. Okay.
Yeah.
Do we submit the project as a PDF? That is correct, Aaron. Challenging but not too terrible, says Phil. Yeah. That's where I want it to be. It's challenging, somewhat realistic, but it's certainly not outside of your grasp. It's right there for the taking. I love the real-life implementation of the project. It was really satisfying to finish it. Great! I'm really glad that was your experience. Yeah, I even had fun putting this together and seeing how it worked out for me, and it makes me happy to hear. We're getting into the home stretch, everybody. This is the penultimate week. 2 weeks left. Is the project going well for everybody else? Okay. What do you say we get started? It's a new week. It's Monday. Olivia says almost done. Great. If you guys have questions at any point, shoot me an email, or you can just ask me on Twitch. Whatever works for you. The project is challenging, but definitely doable. It'll be satisfying once you finish it. It's pretty cool. It shows off some of the strengths of state space models. It has like a nice structure when you put it together. And then once you have that state space model, there's a lot you can do with it simulation wise. And there's a lot of built-in commands in MATLAB that make that easy too. But even if you don't have MATLAB, the stuff MATLAB does is it can be done in any other programming language. So it carries over nicely, but MATLAB's a nice way to get started. Okay, so today we're gonna introduce transfer functions. Let me turn down the music just a teensy bit. Transfer functions. Let's first give the definition, and then I'll tell you like what in the world is the point of this. Okay, so a transfer function, it starts with a Laplace transform, which if you've taken, and I think you all have, you've all taken a differential equations course at some point. I think traditionally Laplace transforms are introduced there, but they're a little confusing. So here you have a function of time and then this L operator with a bracket. This is the Laplace transform. So you take the Laplace transform of a function of time. So here's the function of time in here. And so what the Laplace transform does is it multiplies your function by this exponential, e to the minus st, and then it integrates it from 0 to infinity in time. Now, when you do that integral, what comes out is going to be a function of s. What the heck is S? It's a little confusing. S, we call it a Laplace variable. It can be a complex number. And it's kind of abstract, but to make it somewhat physical, it's related to frequency. I'll move this up a little bit. So sometimes when we take the Laplace transform of something, we say that we've taken this function from the time domain into the frequency domain. So it's more studying how something behaves when you, well, as far as dynamic systems go, studying how things behave when we provide different frequencies of input to the system. So, okay, what's the point? So let's talk about what this is doing. A Laplace transform takes a function of time, converts it to a function of S. This is really nice, and we're going to do this later on when you take the Laplace transform of a differential equation. So this Laplace transform converts a differential equation in time. Like the differential equations we work with, they're a function of time. To an algebraic equation in S. Algebraic equations are easier to deal with than differential equations. So it takes a potentially nasty differential equation and puts it into a mathematically more simple expression. Okay, the last point is so Laplace transforms. This allows us to derive transfer functions. And the way I look at it, the most important function of a transfer function practically, it allows us to model real life systems using experimental data. And I'll make this point more clear as we go on, but some systems, mechanical or electrical, if they're simple enough, you can write a differential equation for these systems on paper, like using the techniques we've done so far in this class, like Kirchhoff's loop rule, or Newton's laws, etc. But in real life, sometimes you'll run into systems that are more, well, they're not as easy to apply these rules because you might not be able to physically, let's say it's a circuit, you might not be able to see all the components in this circuit. And so it's hard to model it, or even a suspension system, like the projects on a suspension system, the behavior of those sometimes might be hard to distill it to, like, oh, there's a spring and a damper. In real life, there might be even more going on. So what we can do in that case is run some experiments in real life testing the behavior of these systems, and we get some measurements off of them. It turns out it's not too difficult to take experimental data and fit that data with a transfer function. And a transfer function is a model for a dynamic system. So I guess what I'm trying to say is transfer functions are a good link between real life and mathematical models. Sometimes it's hard to get a mathematical model, but a transfer function provides us a way. I hope that makes some sense, or that it'll at least make more sense later. Okay. So let's start at the beginning. Let's take the Laplace transform of a few simple functions of time, just to show how this works. And then we'll get to transfer functions and so on. So I want to take a Laplace transform of a step input with amplitude A. Let's first give the definition of what this is. Let's call it f of t. It's a function of time, and a step input is 0 when time is less than 0, and then it immediately jumps to its set amplitude for time greater than or equal to 0, and then it just stays there. So that's why they call it a step input, because it turns on from 0 to its amplitude, and it just stays there. Looks like a step. So to try out the Laplace transform, I want to use it on this function of time and convert it to a function of s. So I'm going to use this definition up above. So the Laplace transform of f of t is going to be from 0 to infinity f of t e to the minus st dt. So we're integrating this from 0 to infinity. Well, I know a step function, after time 0, it's just a constant a, right? So we can just substitute a for f of t, because I'm going from 0 to infinity. Okay. And we're going to do this in a couple steps. I'm going to pull, because the a is a constant, I'm going to pull it outside of this integral. Okay, and now we'll actually take the integral. I know it's going to be minus 1 over s e to the minus st, and then we're going to evaluate it at those limits, 0 to infinity. So that's just the integral of an exponential function. Now these limits here, maybe to be really clear, they pertain to the time variable. So we'll put that in here. Okay, because this s variable out in front isn't affected, I'm gonna pull that out just to make this a little easier. T equals infinity, t equals 0. Then we'll come back over this way. So this is minus a over s. And now let's plug in those limits. E to the minus infinity times s minus e to the 0 times s. So I'm just plugging in those limits for t. And we know that e to the minus infinity is just 0. And e to the 0, because we have 0 times s, that's e to the 0 is 1. So I just have minus 1 times minus a over s, so I get a over s. So if you take the Laplace transform of a step input with amplitude a, you get a over s, and so this is a function of s. It's no longer a function of t, as you can clearly see. Now, fortunately, this is the only Laplace transform we're going to actually do in this class, deriving it from scratch, because in practice, if we ever need to use Laplace transforms, you go to Wikipedia, you pull up a table, and you just look it up. I'm going to show you some of the popular ones that we'll end up using in this class down here. So here on the left, we have functions of time, and then if you take the Laplace transform of that function of time using the definition above, it gives you f of s. So we just did that for for this first one, where f of t was a for t greater than 0, and f of s is a over s. So this is a step. This next one is a ramp with slope a. If you went through that same integral process we did up above, you'd get a over s squared. And well, you know what this is. Sinusoid. Other than the step, I would say the sinusoid is the most important one. Going through this derivation for this f of s is actually kind of fun. But we won't do it. If you're curious though, I encourage you to go through it. I've done it a couple times. There's a little trick for that one where you find that you're going in like a cycle and you're like, whoa, I've been here before. And you find that some term is equal to something you did earlier and it looks kind of recursive. But in the end, you get to this. Okay, so The takeaway here, you take the Laplace transform of a function of time, you get back a function of s. And here are probably the most popular functions of time that we'll use in dynamic systems. And so here we have their corresponding functions of s. Okay. But this is where the Laplace transform gets very useful. And it goes back to one of the points I made at the very beginning, that if you take the Laplace transform of a differential equation, it turns it into an algebraic equation. So let's start by taking the Laplace transform of the derivative of a function. So we're going to take the Laplace transform of the first derivative of some function of time x. So this is the definition. The Laplace transform of the derivative is s times the Laplace transform of the variable itself without the derivative minus the initial condition of that variable. You can derive this definition using that integral definition of the Laplace transform up above. But this is what you'll get. Now, this is kind of cool. What if I want to take the Laplace transform of the second derivative of something? Well, it turns out you can use the same definition from up above, because recognize that this second derivative of x is the first derivative of the first derivative of x. Well, so like what I'm saying is this is the same thing as d dt of x dot of t. So I could think of this as just a first derivative term and use this definition up above. So this would be s times the Laplace transform of x dot of t minus the initial condition for x dot of t. You see what I did? So it looks just like that above. I kind of cheated, but not really. And then what you can do, I can take this and I can substitute in this expression from up above. So this is going to be s times s Laplace of x of t minus x naught. So I'm just substituting in that thing. So overall, if I multiply this out, I'd have s squared times the Laplace transform of x of t minus s times x naught minus x dot naught. Oh. And this Laplace of x of t, that's called x of s. Yeah, neat, right? And so down here I can call this x of s. When we transfer to the S domain, we tend to write the variable in like a capital letter at this point. Okay, now I'm going to show you the Laplace transform of the third derivative, and after this, I think you're going to see a pattern. Okay, so the Laplace transform of x triple dot of t. I'm just going to skip right to the end. It's going to be s cubed x of s minus s squared x naught minus s x dot naught minus x double dot. So there's a pattern here. Maybe I'll rewrite the other ones so you can start to see it a little bit. But the second derivative was s squared minus x s of naught. The first derivative, that was s. So I bet just comparing these three lines, you would be able to write what the Laplace transform of a fourth derivative was. You can see if you get the same thing that I'm about to get. So you start with an s to the fourth x of s minus s cubed x naught minus s squared x dot naught minus s x double dot naught minus x triple dot. So look at this. Taking the time derivative of something is the same as in the S domain multiplying that variable by powers of S and multiplying its initial conditions by powers of S. It's a little weird to think about physically, but I just keep going back to functionally what it's doing. It's taking a differential equation and turning it into an algebraic equation. Because on the right-hand side, you don't see any derivatives anymore. You don't see any d dt. I mean, you see, you do see these derivatives, but these are just initial conditions. So you'll just plug some number in here. It's not a function of time. Okay. Let's do an example. So we're going to take the Laplace transform of a differential equation. And once we do this, we're going to be very close to the idea of a transfer function. So we're almost there. Okay. Let's do this example. So I have this second order differential equation. It's got some forcing function and some initial conditions. So let's take the Laplace transform of this. I'm getting bored of using red, so I'm going to use purple. Llama with memory loss says, what are we learning about? We are learning about transfer functions today, which are a very important topic in system dynamics. We use it for mathematically modeling physical processes. And then later, if you really like dynamics, we use transfer functions all the time for designing control systems for like cars, aircraft, whatever. So I should have mentioned that at the beginning as well. Transfer functions are used very often in control systems. Okay. So I'm going to take the Laplace transform of this. We're going to apply the Laplace transform to the left side, and, well, we have to take the Laplace transform of both sides. And we're going to break this up into a bunch of steps so you don't miss any of the juicy details. So this Laplace transform on the left-hand side, it's the same as taking the Laplace transform of the individual parts and adding them up together. And this, like, 2 times x dot of t, you can pull that outside of the Laplace transform. Because the Laplace transform of a constant, you just get back the same constant. So if I took the Laplace transform of 2, well, okay, I don't want to say that. But you can pull a scalar multiplying a function of time outside of the Laplace transform. That's what I should have said. Okay. So now we can use the definitions we just did up above and apply them to all of these derivatives. So if I take the Laplace transform of the second time derivative of a variable, I'm going to have s squared times that variable in the s domain minus s times the initial condition minus the initial condition of the derivative. So that's from this term right here. And then I have plus 2 times the Laplace transform of x of t, which is just s times x of s minus the initial condition. So that came from here. Plus 100. And then the Laplace transform of a function of time is just x of s. And then same thing on the right hand side. I'll just call it capital F of s. All right, let's gather up any similar terms. So I'm going to gather terms that multiply with x of s plus 2s plus 100. So I gathered all the x of s terms together. Let's see. I'm going to gather these x naught terms. I think it's s plus 2. So I'll have minus s times x naught minus 2 times x naught minus x dot naught equals f of s. So let's get x of s by itself. F of s over s squared plus 2s plus 100 plus x dot naught s plus 2x naught over s squared plus 2s plus 100. Great. Okay, so what can you do with this? We started with a differential equation with initial conditions. Oh, speaking of initial conditions, we could plug those in. I know this initial condition is -1 from up above. And this condition is 1. And that's what I meant, that like even though you see like a derivative term here, it's the derivative evaluated at 0, which is equal to some number. So it's not like a differential thing. So what can you do with this? One thing you can do, you can use something called the inverse Laplace transform, which we actually won't do. But you might have done this in your differential equations course. We call it L minus 1 of x of s. And that will give you x of t, which is the solution of the differential equation. But we already know how to solve for the solution of these differential equations. You know, you have the homogeneous solution, you have the particular solution, and in this class, I showed you how to solve that in the time domain. You just leave it all in the time domain. But I broke this into 2 parts just to show you. This is the particular part. This is the homogeneous part right here. So if you took the inverse Laplace transform of this, you could take it of this thing on the left and get the particular solution. You could do it on the thing on the right, get the homogeneous solution, and it'll give you x of t. But for now, we're not going to do this. We are going to derive what's called a transfer function. Which I believe will be the next little box down here. Oh, white space. Okay. So we're finally here. The arrival point. What the heck is a transfer function? Well, I'm going to give you the definition. It is... Okay, so we'll say... I'll just call it like TF, a transfer function. It equals the Laplace transform of your output divided by the Laplace transform of your input. And you take this whole thing and you evaluate it with initial conditions set equal to 0. That's what a transfer function is. Laplace transform of your output divided by Laplace transform of your input. Evaluate that with the initial conditions set equal to 0. Excuse me. Okay. So how about we recycle our result from the previous example, but I didn't define any outputs for the previous example. So now that we've done some state space, you're familiar with an output vector. So let's say I have two outputs. The first output is x of t, and then the second output is x of t minus 0.1 x dot of t. And define input as f of t. So that was just our right-hand side term for this differential equation. Okay. So there's actually two transfer functions we can make for this system, because a transfer function always relates one output to one input. So one possible transfer function is the Laplace transform of our first output, y1, divided by the Laplace transform of our input. So this is y1 of s over f of s. And our initial conditions, we're going to set those equal to 0, because that's just the definition of a transfer function. Okay, so the way I'm going to do this is first we're going to start with the Laplace transform of our output. So looking at this definition I gave over here on the right, that's going to be the Laplace transform of x of t. And so that is equal to x of s. But luckily for us, we have this over here. Oh no, where'd it go? I'm just going to copy this. I'm going to bring it back down here. Okay. I'm going to get rid of some of this. Now remember, for a transfer function, we're going to assume that the initial conditions are 0. So, because we're getting a transfer function, I'm going to assume this is 0. I'm going to assume this is 0. And so this whole term, 0. Because for a transfer function, I'm just going to write it out. For a transfer function, initial conditions are assumed equal to 0. To be 0. So we're just going to be left with this. Okay.
You know what I'm saying? Like, this is what I do for a living, man. And I don't
So our
like
transfer
bullshit.
function,
Like I said, you know what I mean? That's what I'm
y1
trying
of
to tell
s
you right
over f of s, we know that's equal to x of s over f of s, because that's what y1 is. It's just x. So that's going to be f of s over s squared plus 2s plus 100 divided by f of s. So it's just 1 over s squared plus 2s plus 100. All right, let's do this for our second output. So there's a separate transfer function for that one. Y2 of s over f of s. So let's do the same thing. First, we look at y2 of s, which I know is the Laplace transform of y2 of t. And y2, what was that? It's x of t minus 0.1 x dot of t. And this, of course, Laplace transform of x of t minus 0.1 Laplace transform x dot of t. And that's going to be x of s minus 0.1 s times x of s here. I'll include this complete thing. Minus x of 0. But when you're dealing with transfer functions, anytime you see an initial condition, you can assume it's equal to 0. Okay, so with that in mind, it's x of s minus 0.1 s x of s. And this is 1 minus 0.1 s x of s. Okay. So let's get the transfer function. y2 of s over f of s is 1 minus 0.1 s times x of s over f of s. And you know what? From this previous example, we know what x of s over f of s is. It's 1 over s squared plus 2s plus 100. So let's just make that substitution here. And just like that, we have derived our first two transfer functions. Glory. Let's see what we have next. Okay. Once you start working with transfer functions, you're going to hear about poles and zeros. Poles and zeros. Okay. To talk about poles and zeros, I want to bring over the transfer functions that we just derived. Okay, so from last example, y1 of s over f of s is, I can't remember what it was. Okay, 1 over s squared plus 2s plus 100. And y2 of s, this was our other transfer function. What were you? Okay, 1 minus 0.1s. And it had the same denominator. Ooh, my pen better not be dying here. Okay. Let's put a little divider here. All right, poles. Poles are values of s that make the transfer function equal to infinity. So a pole of this transfer function is going to be some value of s that I can plug in to these transfer functions, and it'll make the whole transfer function evaluate to infinity. Okay, so let's talk about this first transfer function, y1 of s over f of s. How can you make this transfer function equal to infinity? What values of s would you need to plug in? What would be your strategy for finding them? Throw it in the chat if you have an idea. How do you usually make something equal to infinity as far as fractions go? One way is to divide by 0, right? Like if you divide a number by a very small number, the result is a big number. And so if you divide by a very, 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 very small number, you get a very big number. If you divide by 0, you get, something undefined or infinite. So how can I create like a divide by 0 kind of situation here? So one way you can find the roots of the denominator polynomial. So what are the roots? Those are the values of s that make the denominator equal to 0. Yes. That is correct. I'm opening MATLAB right now. Roots. This is one way to do it. 1, 2, 100. Minus 1 plus or minus 9.95, let's call it. So the poles are let's call them S1 and 2. And they are minus 1 plus or minus 9.95i. Because if you plug in either one of these, either pair of this root, it's going to make the denominator go to 0. You're going to have a divide by 0 kind of situation. That's why it's a pole. Okay, what about our other transfer function? What are the poles? They're the same, right? The poles are the same because the denominator of these transfer functions is the same. And even if you're plugging in this number into the numerator as well, you'll still have something divided by 0. Okay, let us define zeros. You might already have an idea based on the name. The values of s that make the transfer function equal to, you guessed it, 0. So let's once again look at our first transfer function, y1 of s over f of s, and ask yourself, is there any value of s that can make this transfer function go to 0. This one's a little trickier. I'll put it this way. There are no finite zeros No, because there's no S in the numerator. Good. Like, if we look at this kind of numerator-denominator thing, if you can make the numerator equal to 0, the transfer function will go to 0. But there's also like a tricky way, and this becomes more important in control systems, but there's another way to make a transfer function go to 0, which is dividing by infinity. So for this first transfer function, if I set s equal to infinity, I'd be dividing 1 by an infinite number. And it would go to 0. But in this class, I think we're mostly concerned with finite zeros. So I'll just say there's no finite zeros. Okay, let's look at this other transfer function. What about this case? There's 1 0, right? There is one finite way to do this. If I set s equal to 10, so if you take that s equals 10 and you plug it in there, I'm going to have 1 minus 1, and it's going to be 0. And the whole thing goes to 0. I just wanted to draw a square. Why is it so hard? Okay, we're going to do it just by hand. I just want to accentuate this for anybody coming back later, so the poles and zeros will pop out. Okay. Let's talk about the significance of poles for a second here. And then we're going to take a little break. It turns out poles are related, and you may have already seen this. They're related to a couple things we've done so far in the class. So, okay. Using this same example, from both transfer functions, the poles are minus 1 plus or minus 9.95i. So let's just set that aside. Now, where did we get this? We started with a differential equation. It was x double dot of t plus 2x dot of t plus 100x of t equals f of t. If we find the characteristic equation, it's going to be lambda squared plus 2 lambda plus 100 equals 0, right? Well, that looks familiar, doesn't it? That's the same polynomial, so we'll get those same roots. Now, the last thing, if we were to put this system in state space form and get the A matrix, if I said like my state vector z is x of t and x dot of t, well then if I take the first time derivative of that, I'll get an A matrix times my state vector plus my B matrix times f of t. So this will be 0, 1, 0, 1, minus 100, minus 2. And this will be A. This will be B. And from state space, you already know what to expect. If I take the eigenvalues of A, why don't we do this in MATLAB? Oops. So I'll make that A matrix 0, 1, minus 100, minus 2. If I take the eigenvalues, same thing. As expected. So we have this cool relationship. Everything in dynamics kind of does this. Poles, those are equal to roots of characteristic equation. Really struggling to write. And these are equal to eigenvalues of the A matrix, which are once again equal to the poles. So I hope one of the takeaways from this course as we look at these different mathematical representations is that you'll be able to see that they're all connected, but some representations that we choose are better in some contexts than others. So like state space, it's really nice for simulation. It's really nice for, I think, for a clean way of modeling and representing a complex system. A differential equation, that's good for like Newton's laws. When you start to sum forces, that like just gives you a differential equation immediately. So that's convenient. And then transfer functions we'll find have more utility like in experimental settings and control systems. But if you have one of these representations, you can convert to the others. So like whatever flavor you want. So okay, we got transfer functions here. We have differential equation over here. And over here we have state space. And I think this is the most important connection between all these forms is these roots and poles. All right, let us take a 5-minute break. And then we're going to come back and do some more examples. Sound good? All right, I'm going to turn up these tunes. There we go. So let's say 3:22 Eastern. We're going to boot this up again. right, we're back. All right, let's talk about transfer functions for systems with multiple inputs and multiple outputs. The last example we did had multiple outputs, but it didn't have multiple inputs. So let us look at this system. So this is going to have two inputs. Okay. So I'm going to call my outputs. So this will be my output vector, and there's going to be 3 of them. And let's have them equal to the just these different derivatives of x. And our input vector, we'll call it u of t, and it'll just be u1 and u2. So here's the thing about transfer functions. A transfer function relates one input to one output. So for every input output combination, we can define a different transfer function. One way to visualize it you have your inputs, you have your outputs, and so you can do 1 transfer function, 2 transfer functions, 3 transfer functions, 4, 5, and 6. So we have 6 possible transfer functions for this system. But in general, the number of transfer functions is your number of inputs times your number of outputs. So in this case, 2 times 3 gives us 6. Number of inputs times number of outputs. So just like for state space, if you know how many inputs, outputs, and states you have, you know the size of the A, B, C, D matrices. With transfer functions, you at least know the number of inputs and outputs. I mean, you know the number of transfer functions you could possibly choose. Okay. Okay, now here's one other thing to remember. When deriving a transfer function related to one system input, assume all other system inputs to be 0. So, for example, let's say we're getting y1 of s over u1 of s. That's one of the 6 possible transfer functions. Assume u2 of s equals 0. All right, now let's get into it. Let's do some practice. This will help us get more familiar with transfer functions. Derive all possible transfer functions for this system. So the first thing I do if I'm confronted with a problem like this, I might just write out in advance what these transfer functions could be. y1 of s over u1 of s, y2 of s over u1 of s. Remember, transfer functions are output divided by input, not the other way around. And then I can also have all 3 of those outputs divided by my second input. Okay. First, this is my advice. Get x of s over u1 of s and x of s over u2 of s. The reason I want you to get these will be building blocks for all of these transfer functions. So if you get these right at the beginning, they'll save you work down the line. All right, let's do it. So this is our differential equation. And then you take the Laplace transform. And right off the bat, because we're making transfer functions, we're going to assume the initial conditions are 0. It's going to save us a lot of work, because we're going to set them to 0 eventually anyways. So let's just write it all out. Oh, the music is playing that song from Willy Wonka. I love this song. Okay, just had to take that slight detour. Okay, so if the initial conditions are 0, this gives us s squared s x of s. We're ignoring the other terms. Plus x s of s plus 5x of s equals u1 of s plus u2 of s. Let's group up these terms. S squared plus s okay. Now, we're going to consider these inputs separately. Just like I mentioned in the comment up above, if I'm considering the input U1, I'll consider the effect of U2 to be 0. So I'll have x1 of s over u1 of s oh wait, did I mess this up here? Oh, I missed this 2 in front of u2. Plus 2. So we got to fill that in. Okay. So just to be clear, here I'm considering u2 of s to be 0. That's the only reason I can write it like this. And then with respect to the other input, u2, I'm considering u1 of s to be equal to 0. So this is what I do first. You could have 100 inputs. I get that dependent variable x with respect to each input. And like I said, these are going to be building blocks we recycle over and over again. Okay. Okay. So next. Okay, y1 of s is the Laplace transform of y1 of t, which was, it was just x of t. Well, okay, that's x of s. So that means our first transfer function, let's do y1 of s over u1 of s. Well, that just equals x of s over u1 of s, and we already have that. Done. 1 of 6 finished. And let's continue with y1. I can get the transfer function with respect to u2. So y1 of s is just x of s. So with respect to u2 of s, it's 2 over s squared plus s plus 5. So that's 2 of our transfer functions. Let's move on to y2. So that would be the Laplace transform of y2 of t. But that would be, we defined y2 to be x dot of t. And if we're assuming initial conditions to be 0, it's just s times x of s. So I'll just keep like reinforcing that. Assume initial conditions equals 0. Let me make sure I'm not going really wide here. When I don't have like a guideline, I tend to write bigger and bigger. Let's rein this back in. And make like a guideline over here so I don't go crazy. There we go. Okay. So y2 of s is s times x of s. Let's get our transfer functions then. y2 of s over u1 of s. Well, that's going to be s times x of s over u1 of s. Well, x over u1 is 1 over s squared plus s plus 5, and we just multiply that by s. y2 of s over u2 of s is s x of s over u2 of s. And it's just going to be this. Beautiful. All right, let's do the last one. finally, y3 of s is the Laplace transform of y3 of t. And I think that was just x double dot of t. Yep. And if we assume the initial conditions are 0, that's s squared times x of s. So let's make those transfer functions. S squared x of s over u1 of s. And we're just using the x of s over u1 of s that we got earlier, and we're just using it over and over again, recycling it. That's why I like to get that right at the beginning. All right, that's all 6. I'm going to number them. 1, 2, 3, 4, 5, and 6. Let's quickly blast through these and get all of the zeros and poles. Okay. Zeros, poles. So poles are the values of s that make this transfer function equal to infinity. We know that the way to get it is find the roots of the denominator. Let's go to MATLAB. Roots of s squared plus s plus 5. So minus 0.5, 0.5 plus or minus, let's call it 2.18i. Something about transfer functions for a given system. This system has 6 transfer functions. All of the transfer functions are going to have the same poles. You know why? Because, like I said earlier, the poles are the same as the roots of the characteristic equation. Now, transfer functions are based on inputs and outputs, and however you define the inputs or the outputs, that doesn't change the roots of the characteristic equation. Because how do you get the characteristic equation? It comes from the homogeneous part of the differential equation. That doesn't depend on inputs, and it doesn't depend on outputs. So that tells us that, like, you could come up with any input-output combo. It's not going to change the underlying characteristic equation, and that means every transfer function you make should have the same denominator. That's one way to check your work. And they should all have the same poles for a given system. Zeros will be different. So all I did, I went through here and I labeled every single one to have the same poles as this first one. Okay. Let's look at these first 2 transfer functions. Do they have any zeros? Do they have any values of s that would make this transfer function go to 0? And the answer is, well, yes, if you plugged in s equals infinity, but I'll just say this. There's no finite zeros. There's nothing other than infinity that I could put in there that could make this go to 0. What about these two? This is an S up here, by the way. Well, the 0 here, if I plug in S equals 0, those will go to 0. Now this last one, be careful, because you might look at this, be like, okay, S squared, S equals 0 is the 0. However, it's important that there's 2 zeros. It's just like a repeated root. Something like that. Think of it that way. But it has 2 zeros, not 1. 2 zeros at S equals 0. That becomes important in control systems. If you neglect one of these, you could make a control system that turns out to be unstable. Okay, let's see. We've covered quite a bit in less than 2 hours. We did transfer functions. Good gravy. If you're following along writing, your wrist might be sore at this point. But you know, I think this is a nice place to wrap it up today. So I mentioned how, could we think of the 2 zeros like plus minus being 2 roots of a square root? Phil says my brain is fried. Okay, could we think of the 2 zeros like plus minus being 2? I'm hesitant to say yes on that because if there was like an S cubed on top, then it would just be 0, 0, 0. So I would think of it more like a repeated real root. Now zeros are interesting because I should have written this earlier. Zeros do not affect the stability of your system. Like poles, roots of characteristic equation, eigenvalues of A matrix. Well, they're all the same thing. These, you know, they affect your stability. They affect your settling time, oscillations. Like, they tell you all of that stuff. That's why we call it the characteristic equation, because it's telling you characteristics about a system. Zeros, on the other hand, they do not affect stability. So what about a pole tells you stability? Well, if a pole has a real part that's positive, then you know your system is unstable. If a zero has a positive real part, that doesn't mean you're unstable. So what do zeros do? They're kind of funny. Like they do different things. One thing that they do, well, okay, I'll say generally they do affect some transient dynamics. For example, they can affect overshoot, and they can create undershoot. We haven't even talked about undershoot, but let me show you what it looks like. Let's say I have time, and then I have some output that's a function of time. So if you have a first order system and you give a step input, it looks something like this. And it goes to some steady state value. It has some time constant, etc. Now, if you start adding zeros, you can find that maybe your system undershoots first and then comes up, and maybe it overshoots and then does something like this. So this, we've seen this before, that's overshoot. But this kind of initial undershoot where it goes down before it goes in that direction, that can be caused by zeros. So if you see something like that in a step response, well, that gives you a clue. Yeah, they're funny little things. I'll see if I can come up with more like practical examples of what zeros do as we go on. My plan for next class, let me show you. So I have this motor attached to a wheel. And so one part of this class is studying how systems behave when they're like mixed. Like a motor, it obviously is mechanical, but it has an electrical part as well. So this is an electromechanical system. And so I'm going to talk about how we model this. But this, like I said at the beginning of class, sometimes it's hard to model something because you can't see everything that's going on here. Like this motor, there's circuitry in here. There's coils of the motor, but I'm not going to pop this thing open and look at all of that. And it's so an important part of a motor is its resistance, its inductance. But even if I like hook up a probe from a multimeter and try to measure the inductance and the resistance, that's hard to do. So I'm gonna try to do an experimental technique where we provide different inputs to this system and we see how it reacts. And then we'll try to fit that with a transfer function. And the transfer function will be our model. So we're going to try to model this real life system. Play around with it some in this class. But that's my plan, to try to showcase the utility of transfer functions. But that's pretty much it for today, guys. I'm gonna hang around for a bit. Any questions you have about the course, about the project, any miscellaneous dynamics questions you have, they are all welcome here. You are welcome to hang out. And I hope you're doing well. Phil says, any hints for MATLAB why the legend colors wouldn't match the graph colors? Yours don't match? Do mine match? So, okay, Phil, sometimes that can happen. Like, that's happened to me when you have a blue and orange legend and an orange and yellow graph. Okay. A blue... How many lines do you have on your graph? You only have the orange and the yellow? So, okay, but first I'll tell you... Actually, let me show you in MATLAB. This will make more sense. Let's go... Okay, so let's make just a random time vector. And let's make 3 different outputs. I'll say sine, sine times t, and we'll do that. And then I'm going to stack these side by side, which is something that you have to do in the project for your inputs, I believe. Okay, so if I go figure, I can plot t versus y, and let's see what happens. Okay, let's just say in class 6/22/2020. All right, let's run this. Okay, so I have 3 lines, right? So let's throw a legend on here. If I do y1 y2, like if I only put 2 on my legend instead of 3, well then it has a blue and a yellow, a blue and an orange in my legend, but I actually have 3 lines. What I'm wondering, Phil, is maybe What's the significance of the colon? Which one? Are you talking about this? Oh, these guys? Oh, this just says, this is a time vector that starts at 0, and then it goes in increments of 0.01 all the way up to 1 as the final value. So this time vector will be 0, 0.01, 0.02, 0.03, all the way up to 1. What I'm suspecting happened, you said you see an orange and a yellow line. I'm guessing that there's also a blue line, but that it's like at 0 and you can't see it. Or maybe it's not a number or something like that. Because if I do, let's see if I could artificially do it. What if instead I say y1 equals zeros and it's the same size as t? And then I'll just like comment this out and I'll run it again. Well, actually you can still see y1. What if I do... How do you make not a number? It's an easy way to do that. Does that work? Oh, I did it. So now there's only 2 lines on here. What I would say is, can you check, like, I'm plotting y, right? So if I plot y, or if I just print y to your workspace, I wouldn't be surprised if that first entry says something like this. Can you test that? You don't know how? I Google everything. Yeah, we do use MATLAB quite a bit. I think it is a prereq actually. Because MAE 376 is a, I guess it's a co-requisite. But even prior to that, EAS 207? Which one is it? But there's a sophomore class that... You never touched it before this course? Did you take EAS 230 or what is it? Yeah, that's a MATLAB course, right? Yeah, you have to take 230. But anyways, I'm just trying to recreate your bug. And this happens to me when some of my data isn't what I expected. to be. So which part of the project are you getting this graph for? Like, is it for the gravity part? Oh yeah, you said you're doing part 3, right? Oh, that might have been a transfer credit. Okay. So part 3... So you're trying to get a graph like this. So it should only be plotting 2 things, but if you get a yellow line, that means you're plotting 3 things. You're almost completely inverted. Interesting. Let me try something else. Orange along the bottom, blue shifted, 1 sine curve. And it's all positive. Interesting. Okay, can you do something for me? Check the eigenvalues. Okay, yeah, email me a screenshot, but check the eigenvalues of your A matrix. Are all your roots stable? That might be something to check. If they go positive, okay, all real parts are negative. Okay, good. If it goes positive, I mean, there's a couple things. Like if you... Are you giving a positive number for G? Like this model is designed so that G should be like a positive step. Okay, you did that. Maybe some. Did you send me? I'll check my email. Oh, you just emailed me? Let's take a peek. Deflection. Okay. Okay, so I think it's plotting... I still think it's plotting 3 things. What I think is that I think the orange line is on top of the blue line. And that's why you can't see it. Let's see. Let's go back to this. Okay, how about you try... I'm curious about this. You have this y variable, right? That's what you're plotting. Can you check the size of Y? Like this. Just type size Y.
Sheriff, if you think I have any qualms about killing this kid, you couldn't be more wrong.
So you have 3. Okay, that means that you have 3 outputs, but there's only supposed to be 2 outputs. Oh wait, there is 3. Oh, never mind. Okay, but 2 of the outputs should be on one graph. Oh, you know what? I think this is just because you're showing all 3 outputs on the same graph. You should have 2 outputs on one graph and the third output on the other. I think yours is correct, actually. Or it's almost correct. I think I know what's going on with yours. Yeah, your problem is you need to do the first 2 outputs on one graph and the third output on its own graph. Yeah. Yeah, that's the problem. So what 3 variables am I plotting? Okay, so in your code right now, you're plotting y1, y2, and y3. So your y... Let's go back to this. When you do the step command, and in your code, basically you have this variable y, and you said it's 1329 by 3, right? So that means it has 3 columns, and each column has 1329 rows. So it's similar to this. So if you go plot ty, it's going to plot t against this matrix y, and it's going to take each of the columns of y and show that as a separate line. So because this matrix has 3 columns, it does 1 line for each column. So in here, I tell you how you can plot each of them individually if you want. For example, if you want to plot X, you access the first column by itself. Or if you want to do the second column by itself, you do that. So on one plot, I want you to do the first two columns, and you'll get this. Like, these are the first two outputs. This one is the third output. No, you're not missing any. In the plot you sent me, all three of them are there. It's just that the first two outputs are so small in comparison to your third output that it looks like the first two are at 0. You only see the orange line because the blue line is underneath it. If you zoom in on your plot, you're going to see that there's a blue line there as well. Try it. Zoom in on there. I could even replicate it for you. Let's see. Like if I do something like this. Wait, is there... actually, it's similar to this. If I do like... I don't know. This will look pretty much the same. See this? You see the yellow and you see the orange. But if I take that zoom in thing and I zoom in on these bottom guys, oh, there is the blue. It's both here. You're gonna see the same thing on yours. It's just when it's all zoomed out, the orange is on top. It's because the third output is so large in comparison to the other two. This has consumed my entire day. It's involved, but it's satisfying. You're actually very close. Like what you're dealing with right now is just, well, I already explained it to you. But once you fix that, you're gonna see that your plots are probably in good shape for part 3. And if you can do part 3, part 4 is not a problem. So if you use hint 2, yes. Why am I getting all 3 Ys? Okay, so I try to explain that in here. So okay, you have 3 outputs, but you also have 3 inputs to this system. When you use the step command, what it does is it says, okay, I'm going to give a step input for your first input variable. I'm going to give a step for R dot as well, my second input, and I'm going to give a step for G. So, like physically, if you go back to this diagram, the step command introduces a step to like a road bump, as well as G, like all 3 of those, it tests those. But we're just looking for the effect of G, right? So I don't want to see the step inputs for my other 2 inputs. So that's why so what am I trying to say? Step gives you a 3-dimensional matrix in this case. It gives you a matrix of outputs for each different input. Actually, this would probably be easier if I draw it. We're gonna draw. Okay. So you have 3 inputs. You have R of t, so the position and velocity of the vertical movement of the road. And then I also have gravity. If I do a step from gravity, I'm going to make a 2-dimensional matrix, but it's kind of going to be in perspective. We'll see if this works. And it's going to give my first output, like in this first column, Y2 and Y3. And then like it has 1 row per time instance. So a step just from G generates a 2-dimensional matrix. But when you run the step command, it also does a step for the road velocity. Maybe I'll like put this over here. And it makes another matrix for that. Just considering that by itself. And it makes a matrix for that. And this one makes even another one. Now, when you call the stepped command, it smashes all 3 of these matrices together. So when you do YT like equals step, the Y that it returns is these three matrices all put together. So it's three-dimensional. Three two-dimensional matrices all slapped together. However, we're only interested in this one. The step input from gravity. If you want this matrix by itself, you have to say, give me the third matrix from Y. Like, that's why there's like this third dimension. This is the matrix number. Like, this one is matrix number 1 from the first input. This one is matrix number 2 from the second output, and this one is matrix number 3. So when you run this command, like you said, the size of this is 1329 by 3, right? Because it's got 3 columns. So if we plot TY, how do we get W? Well, when you plot like figure 2 in your project, like this one, right? No, you're plotting on your graph, you're seeing this line that's on figure 3. And then these other 2 lines are so small in magnitude combined compared to that other line that they're at like 0. You changed, my y-axis is off by a factor. Yeah, that's probably because in your code you did a step command, but you didn't change the amplitude to be 9.81. You just did a unit step. So your unit step is giving like 1 meter per second squared instead of 9.81, because you'll notice yours is off by close to a factor of 10. That's because you didn't do a 9.81 amplitude. And that's hint 4. The step command in MATLAB calculates the unit step input, where the amplitude of the step is 1. But in the case of gravity, the amplitude of the step is 9.81. So to get accurate results, you need to use the scaling property. I changed it. Y-axis is 1,000 times off. For which one? For like the first two outputs? Zero to 0.025. Check out this part. Include both of these outputs on the same graph. Convert the units to millimeters. Did you convert to millimeters? The original values for these units are in meters. I don't define those variables, so how can I convert them? Well, sure you can. Because, let's go over here. So, like, let's say that, I don't know, like I got some response in here, and this is in grams. I could say Y converted is, let's say I want to go to kilograms. I could go Y times 10 to the minus 3. And then I could plot Y converted. There. Because you have the numbers, so you can just convert those numbers. It's getting kind of overcast outside. It's supposed to rain? What's going on here? Whoa! 60% chance of thunderstorms, it looks like? Can you look at the code picture I sent you? I don't define Y anywhere. What about line 20 And what about line 21? Where you have y equals? That's called defining. Anytime you have an equals, you're assigning a variable to be what's on the right hand of the equal sign. The line where you define it is line 20. You define y as the output of the step command. Then on line 21, you say, well, now I'm redefining y to be the third matrix of the original y. Okay, got that. Just missing W. W should be this second column of Y. Well, to redefine Y. Can you run two plots on two graphs? I'm not sure what you mean by that. Two plots on two graphs? Two plot commands on one figure. Sure. There's different things. Let me show you a couple different ways. Okay, so I got this Y. I got 3 columns. Let's say I want to plot the first and the third column or something. So I could say let's do the first 2 columns actually. Oh yeah, you can do this. You can like chain them together like this. Something like that. Yeah. You can also do, okay, cool. Oh, snap! Nice. Told you were close. Yeah. Yeah, that'll work. You can include those JPEGs in your PDF. Got like a tight muscle in my neck. No, thank you.
relationship isn't achieved, that's when the sword becomes nothing more than an evil weapon, serving no one. For that reason, I'm selective about whom I'll work for. I simply have no other choice.
I see. Then let me ask you one question. In all your years forging weapons for other warriors, how many have inspired you to create such a weapon?
All right.
I guess in all my years,
That's it for today, everybody. I'm going to be back for office hours tomorrow at the usual time, 4 to 5 p.m. Eastern.
I forged the finest blade I could, employing all the skills I had available at the time.
Thank you for your time. Thank you for your attention.
As a fellow swordsman,
It
you
is a
must admire
privilege
his.
to do dynamics
What
with you.
more can you tell us about him?
Have a good night.